Assalamualaikum and hi to all viewers. My name is Nur Afifah Md Yusofd with matric number A18SC0184. Today I will be presenting about the method development of optimization of instrument condition for the analysis of mercury, selenium, antimony and also arsenic by the atomic absorption spectroscopy. As we know that the chemical vapor generation atomic absorption spectroscopy is widely used for the trace analysis, specifically for the arsenic, selenium and antimony for the hydride generation, while the cold vapor atomic absorption spectroscopy is for the mercury. By improving the instrument parameters such as reagent flow rate, sample flow rate, argon flow rate, acetylene-OA ratio, concentration of reagents and also the read delay time, this could improve the sensitivity and reliability of the result as well as the recoveries. Basically, the flow rate of the reagent and sample was affected by the tension on the peristaltic pump and also the size of tubing. So, the hydride generation technique separates the analyte from the matrix by the conversion to the volatile hydride, which provide a pathway for the trace analysis of the element, which can be determined by the conventional method. The sensitivity of this technique is due to its ability to determine the trace levels of metals at the wavelength below 200 nanometer, which this region is considerable with spectral interference of radicals in conventional flame AAS. Hydride generation technique involve three processes, which are the hydride generation and the release of element of interest from the sample solution with the aid of reducing agent. Secondly is the hydride collection, and the third one is atomization. The factors that will influence the optimization of the hydride generation AAS are the concentration of the acid, the concentration and the type of reducing agent, the flow rate of the carrier gas, the flow rate of the reducing agent, the flow rate of the acid, and also the read delay time of the sample. On the other hand, the cold vapor AAS is the most sensitive method for the mercury determination compared to flame AAS since it gives more sensitivity. The principle of this technique is the titanium chloride as the reducing agent is used to convert the metal ion of mercury to gas, which produce a higher analytical absorbance signal. The mercury with high vapor pressure is liberated and entrained in an inner gas of argon and then be transferred into the optical path of the atomic absorption spectrophotometer and then absorb light. In order to increase the transport efficiency of the gaseous mercury, several optimizing parameters should be considered, such as the concentration of the reducing agent, the flow rate of the reducing agent, the flow rate of the sample, the flow rate of the purge gas, and the read delay time. For the experimental, the instrumentation and materials be used were such this. In 50 ml of volumetric flask, the calibration standard of 10, 30, and 50 ppb of each metals were prepared to be analyzed. The 30 ppb standard of each metal was used for the optimization of the instrument parameters. This is the schematic illustrating diagram of the optimization parameters for both HGAAS and CVAAS. This is the range selected for each parameter. Note that the deionized water was pumped through the entire system for 60 seconds between analysis to prevent cross-contamination. The VGA77 is equipped with two flow rate adjustments, one for the sample and one for the reducing agent or the acid. In order to regulate the flow rate, the adjustment knob was tightened or released to modify the flow rate. Just like I have mentioned earlier, the internal diameter of the pump tubing also have to be varied to control the flow rate. The tubing used for the reducing agent and acid were 0.63, 0.67, 0.76 mm, while for the sample were 2.28, 2.54 and 2.92 mm. To regulate the flow rate of the acetylene gas to oxidant, the temperature of the acetylene flame was optimized for the HGAAS, while flow rate of argon used in VGA77 was adjusted from the flow gauge on the cylinder. The optimized conditions for each parameter were determined from those that produce the maximum sample absorbance. So this is the table for the optimized condition for the parameters. The optimum concentration for the reducing agent for the arsenic and antimony was 0.6% weight over volume sodium borohydride in 0.5% weight over volume sodium hydroxide, while for the selenium, the reducing agent optimum concentration was 0.1% sodium borohydride in 0.5% weight over volume sodium hydroxide. While for the mercury, the optimal concentration for the reducing agent is 25% weight over volume stannum fluoride in 20% volume over volume hydrochloric acid. The optimal acid condition was found to be 5 molar hydrochloric acid for arsenic, while 10 molar hydrochloric acid for antimony and selenium. The optimal flow rate for the reductant and acid for all metal was found to be 0.96 ml per minute. The maximum signal was obtained for all sample flow rate were to be in range 6 to 7 ml per minute. For the optimum argon flow rate for the arsenic and antimony was 0.2 ml per minute, while for the selenium and mercury was 2.0 ml per minute. Other than that, the instrument delay time controlled the flushing time between samples to remove the anterior ion, which caused the memories effect. The optimized instrument read delay time for the mercury was 70 seconds, while for the selenium, antimony, and arsenic was 20 seconds. To conclude, the optimized instrumental condition do give the superior recoveries when used to measure volatile and hydride-producing metals, just like in this table. So, higher sensitivity and reliability on the data we can obtain.